Thank you very much, Professor Arau. Can everyone hear me okay?
Yes.
Yes.
Okay, so let me share my screen. Buenos dias, amigos. That's the extent of my Spanish, unfortunately. My daughter-in-law is from Peru, so if she were here, she could be helping me with some of the translation. But it's a privilege to have this opportunity to speak with you on your 30th anniversary of CENIDET. And I'm honored and flattered that Professor Arau has extended to me this invitation to participate in your activities. I was reminded during Jaime's discussion of my background that it was in 1993 that I was on tour lecturing, and when I went down to CENIDET, and Jaime was my host down there, and it was my first and only visit to Mexico, unfortunately. I hope at some point I'll have another opportunity because my visit to CENIDET was very memorable, very enjoyable, and I was very pleased to have had the opportunity to do it. And so I'm also very pleased now to participate in your 30th anniversary. So what I would like to do is give you a sort of a two-part presentation. I'd like to show you how power electronics has evolved, solid state power electronics, and how it has evolved particularly within the IEEE. And after we do that, I'd like to talk about some of the exciting opportunities that exist for power electronics in the application area, and just a little bit at the end about some of the technologies that I think are going to make a major impact on how power electronics impacts our future. So let me make sure this is going to work okay. How do I change? Okay, so the advent of solid state power electronics really began in 1957 with the invention of the SCR. This was invented by General Electric in upstate New York at a town called Clyde, a very small town on the Erie Canal, actually. And a few years ago, the Power Electronics Society inaugurated its first memorial plaque commemorating this particular invention at Clyde. So it was very important that this invention took place. And it was such an important invention that within 5 years of the invention, there were 4 books, hardcover books, that were published specifically dedicated to the use of the SCR. Many of you probably are familiar with the SCR manual, at least those of you who are my age or maybe a little younger. And the SCR manual, here's the first edition of it. For many of us, the SCR manual was the Bible for power electronics. It was where many of us learned how to use SCRs and some of the physics of semiconductor devices applied to power. Shortly after the invention of the SCR, shortly after the invention of the SCR, the first commercial product came out, and it was a light dimmer from Lutron Electronics. I believe this was the very first high volume commercial product employing an SCR. It came out in 1961, which was only 3 or 4 years after the invention of the SCR. Lutron is still in business, still makes high quality lighting control systems, but unfortunately they don't use, or maybe fortunately, they don't use SCRs anymore because the SCR in many applications has been displaced by field effect and other transistors. So in 1957, Texas Instruments came out with one of the first silicon power devices, the TI-389. But this was not a very good device, and it never really became practical. And until 1965, there was really no good silicon power device until RCA developed the 2N3055. Now, many of you might know about the 2N3055 because it was a ubiquitous device. It was used in many applications, but because it was not a high frequency device, it had an FT of only 1 megahertz. So it wasn't very good for switching power supplies, but it was used extensively in linear regulators and in audio amplifiers. This device actually is still available if you want to use it. People are still manufacturing it. It's a rugged device. The next thing that happened is that the power electronics field began to be a field that had significant practical applications. And the very first conference devoted to solid state power electronics was the Power Conditioning Specialist Conference, abbreviated PCSC, which was held in 1970. This conference was principally a conference devoted to aerospace applications. It was sponsored by NASA, and it was held at NASA's facilities down in Maryland. And it had an organizing committee that consisted only of a half a dozen people. Maybe some of you recognize some of these names. And the table of contents consisted of only 30 papers. Many of these papers were devoted to space applications, and many of them were some of the first papers that described some of the switching converters that we are using today in various forms. The PCSC, which was held in 1970, became the Power Electronics Specialist Conference 1 year later, in 1971. I'm sure that many of you in the power electronics area have been to a PESC conference. I'll tell you when PESC ended in a little bit. But the PCSC was sponsored by the IEEE's AES Society, the Aerospace and Electronic Systems Society. In 1973, 2 other societies joined as sponsors of PESC, the Electronic Device Society and the Industry Application Society, which began to show you that power electronics was spreading out its impact in areas other than aerospace engineering. In 1973, Bill Newell, for whom the Newell Prize, the IEEE Field Award, the Newell Award is named, presented a paper that essentially said, look, power electronics is not a unique field. It is a field that incorporates power, it incorporates electronics, it incorporates control, it incorporates machinery. And so to really look at this field and to study this field, one needs to be fluent in a lot of different disciplines. And this was a paper that had a significant impact on how the power electronics field evolved. In 1978, INTELEC was formed. INTELEC was a conference that was focused on solid state power electronics in the communications industry, in the telecommunications industry. This was a major user of power electronics after the aerospace industry. And there was a dedicated conference that was started in 1978. And a fellow named Joe Swazi was the very first chair of that conference. Then in 1983, A group of us, about a half a dozen of us, decided that really power electronics needed its own representation within the IEEE. And so we petitioned the IEEE to form the IEEE Power Electronics Council. And that was formed in 1983. In 1986, we published the first transactions on power electronics under the auspices of the council. And we also formed a new conference, APEC. Now, we had PESC, which was still ongoing, but PESC had become a conference that was mostly dedicated to research. And it was populated largely by academics and also researchers from industrial laboratories or government laboratories. And we felt that there needed to be a conference that was specifically tailored for the practitioner, for those who were applying power electronics in industry. So in 1986, another group of us, there were about half a dozen of us, got together and formulated some ideas for how we would form a conference that addressed the practitioner. We went to the IEEE and we said we'd like to do this conference. And I think we started our discussions in something like the end of 1985. So it was sort of like maybe around October or November. And the IEEE said, well, you really don't have time to put together a conference. We wanted to have the conference in 1986 in the fall. And they said, we don't think you can do it. And we looked at each other and we said, yeah, I think we can do it. And so we continued to plan. And here's the conference committee. You might recognize some of the names on here. Dave Middlebrook was at Caltech. Tom Wilson Jr. was at AT&T Laboratories. Actually, I think it was Tom Wilson Sr. who was also part of our activities. So we all got together and began planning this conference. We didn't have much money in our budget. So we had to use an off-site classroom that I show here for our first meeting. So in 1986, we held the first APEC. There were 5 seminars. It was the first time we had seminars at a conference, and there were only 35 papers. Then in 1988, we formed PELS, the Power Electronics Society. So the council transitioned from being a council, which had very limited autonomy, to becoming a society where we were fully autonomous. This was not an easy transition because there were a number of existing societies, in particular the Industry Application Society and the Power Engineering Society, who felt that they already represented power electronics. So I had to work with those societies at a meeting down in New Jersey of the IEEE, and we got them to vote to establish the Power Electronics Society over their objections. So in 1988, the Power Electronics Society was formed. And so here's the rest of the timeline. The Power Electronics Society was formed in 1988. In 1999, the European Power Electronics Society was created. In 2008, the last Power Electronics Specialist Conference was held. And at that conference, by that time, the conference had grown so that there were over 850 papers in 2008 in that last conference. Then in 2009, the ECCE was formed. The Energy Conversion and Control, keep forgetting what ECCE stands for. I just use the letters. That was formed in 2009, and the 35th APEC was held, unfortunately, it was held virtually last year, and it had a huge number of papers and a huge number of seminars. In fact, I think the conference has become too big. It's too hard to navigate if you're there in person. So there's where we are with power electronics within the IEEE. So I'd now like to talk about where we're going. So where are we going? There are a number of emerging and growing applications, and these I think you're all familiar with. Transportation is a huge application with electric vehicles and other other vehicles being electrified. The electric utility industry is using more and more power electronics to control the grid. Communications, consumer goods now almost all contain some element of power electronics. Industrial controls is all power electronics, and of course, robotics would not be anything, wouldn't be even close to where it is today without power electronics being part of the system. And the drivers of the future of power electronics, I list here are some of the things I think are the drivers. Integration and packaging is critical. Wide bandgap devices, we'll talk about briefly at the end of my talk, are providing opportunities for higher temperatures, higher frequencies. Higher frequencies bring down sizes, higher efficiencies bring down sizes, lighter weight, new battery chemistries are critical for some of the applications that we see on the left. And of course, there are new materials that aren't just semiconductor materials, but there are new heat transfer materials and mechanical materials for packaging. So let's talk a little bit about some of the applications and what's going on with them. So here's a picture of the Tesla Model 3 integrated motor. And integrating the motor and the control, the motor and the drive, has been a goal of motor designers for a long time. This has sort of been a holy grail for decades. And here we see an integrated motor and its drive using silicon carbide devices. And I think Tesla has done a remarkable job of engineering in all aspects of their vehicles. Unfortunately, I can't afford a Tesla yet. Here's another picture of what this integrated machine looks like. This is not the Tesla machine. This is one that is an ongoing research project at a number of universities, Ohio State University, University of Wisconsin-Madison, and University of Maryland under a NASA project. But it's a 1 megawatt machine with the drive integrated, as you see, around it. This is, of course, still in its design phases, but it's a very exciting development. Another very interesting development that was presented last year at the Hanover Fest, the Hanover Fair in Germany, was a completely 3D printed motor stator. Now, I have the picture here, but I haven't any idea how this works or what aspects of the stator this is. But what it does represent is that 3D printing is going to be playing a more and more important role in power electronics packaging, in particular with respect to machinery. Another very fascinating area, but one which is only slowly beginning to have an impact, is solid-state transformers. Now, the transformer you see on the left here, which is a transformer on a utility pole that converts something like 7 kV down to the voltage used by residences, In the US, that's 120 or 240 volts, 60 hertz. That's a very inexpensive device. You can weigh it, and then you know how much it costs by the pound, because it's mostly iron and copper. On the right, you see a schematic of one manifestation of a solid state transformer. And of course, all a solid state transformer is taking AC at one voltage, converting that AC at that frequency, in this case 60 hertz, to a high frequency, then transforming the voltage levels through high frequency transformers, and then down converting that voltage and frequency to the line frequency required, in this case, again, 60 hertz. So you start out 7.2 kV AC at 60 hertz, you wind up with 120 volts at 60 hertz with a transformer that is much smaller, much more efficient than the one you see on the left. The differential in cost is overcome to some extent by the fact that such a transformer, a solid state transformer, also provides you with control capability, which you do not have with the transformer you see on the left. Now, some of these transformers, the conventional transformers, have tap changers, which allow you a very limited degree of control. But with a solid state transformer, you've got almost unlimited control to exercise things like voltage lift or load shedding or browning out parts of the grid if you're overloaded. So there are benefits that compensate to some extent for the increased economics. And one of the interesting things I found is that the solid state transformer, as far as I know, was invented first by Bill McMurray. Many of you probably have heard of Bill McMurray. He was a very, very prominent researcher at General Electric's Corporate Research and Development Laboratory in Schenectady, New York. One of the inventors of the McMurray-Bedford inverter, which used SCRs in motor drives. But this was a 1969 patent, and I think you can see very clearly how the solid state transformer works. The switches essentially provide a carrier frequency, high frequency, that is then modulated by the input waveform and then demodulated at the secondary to give you back the frequency that you want for the load, converted, of course, by the turns ratio of the transformer. So I thought this was a very interesting piece of history. So what about electric vehicles? It is truly amazing to me that the electric vehicle has become such a dominant force today in the auto industry. Every auto manufacturer that I know of is now manufacturing electric vehicles, and many of them have said they are going to manufacture nothing but electric vehicles in the near future. So here are a few news paper announcements from a number of manufacturers. General Motors says they're opening up a new plant to do just electric vehicles. The United Postal Service is buying a whole bunch of 10,000 electric trucks from a United Kingdom startup named Arrival. Peterbilt, which is a big truck company, is even electrifying a Class 8 truck. This is a Class 8 truck, if you're not familiar with the nomenclature. It's your traditional tractor trailer. Tesla is also exploring electrifying a Class 8 truck. This is a big deal. what's going on here. Let me see. Huh. Buses are another vehicle that's being electrified, and 12 cities say they're going to buy all electric buses starting in 2025. Now, here's something that really shocked me. We are going to see electric airplanes, commercially flying electric airplanes. Toyota, as you see here, is investing in what they call flying taxis. Hyundai is partnering with Uber on another electrified taxi. What they propose here in their design is one that'll go 180 miles per hour and has an electric range of 60 miles, 97, almost 100 kilometers. And they say it'll only take 5 to 7 minutes to charge. Here's another one. Personal Airline Exchange is a company, it's called PAEX or PX, is buying 50 electric hybrid commuter airplanes. Now, I'm not sure what the hybrid component is or why a hybrid airplane actually is better than one that is completely fueled by petroleum, because unlike a car, an airplane is generally cruising at one engine speed, but nevertheless, that's what they're doing. And Cape Air is a company, an airline company on Cape Cod, which is part of Massachusetts. It's where I have a summer home. They are going to be flying all electric airplanes. And this is a mock-up of the, actually it's not a mock-up, it's an actual one of the airplane that they're going to be flying. It's called, the model is called an Alice. And here are the specifications for that airplane. It's got a range of 540 nautical miles, which is something on the order of 650 statute miles. Speed of 240 knots, which is about 300 miles an hour. And here's the interesting statistic. Its mean takeoff weight is 6,300 kilograms. The battery weighs 3,600 kilograms, which is 60% already of its mean takeoff weight. So it's a 920 kilowatt hour battery. Of course, lithium, nickel, manganese, cobalt chemistry that they're going to be using. That is one huge battery. So that's it for traditional airplanes being electrified. But let me show you something that I think is fascinating. It is electro-aerodynamic propulsion. This is a propulsion technology that is being investigated by the Aero and Astro department at MIT. And my laboratory participated in providing the power electronics to produce the propulsive force, the propulsive ion force for this system. Yo Hee, who was one of my graduate students, did this for her doctoral thesis. And what I show you here is essentially an aerodynamic propulsion system. There's an electrode here, an emitter, which between these two electrodes emits an ion cloud. And down here is a collector which attracts the ions down here. If you take a look over here, you see the voltages. The creation voltage is only 3 to 4 kV. It's AC at 10 kilohertz. But the propulsion voltage, that which provides the attractive force on the ions, is 40 to 80 kV at DC. Right? So the ions from here are attracted to the collector, and of course provide thrust in the upward direction. So I'm going to show you now 2 videos of the effectiveness of this scheme. What we have here is, this is an airplane in here. This is an MIT gymnasium. And there are going to be 2 videos. The first one is going to be this airplane launched from its ramp here with no propulsion power. So you just see how far it goes gliding. So watch it carefully. So you see it goes maybe 50 feet or so. Now what I want to show you is the same aircraft here, but this time the propulsion system is going to be energized. So watch carefully, because this video is in 3 parts, since they needed 3 cameras to catch the trajectory across the gym. So the aircraft is going to fly straight across this gym until it's brought down just before it runs into the barrier at the end. So, and in fact, if you look up here, you'll eventually see how far it went. So you see that was brought down so that it wouldn't crash into this barrier, this netting, and damage it. And if you look up here, you'll see that the total distance was 56 meters, which gives you an indication of how practical this scheme is. I think it's really fascinating. But once again, that propulsion scheme would not be possible without power electronics. It was a critical element to make that happen. Now, what about robots? Now, this is an interesting little video. These are robots that were fabricated in the mechanical engineering department. Whoops. In the mechanical engineering department, with assistance from some of our power electronics and machine folks in our laboratory. And I just want you to see their behavior.
Whoa.
How do you like that recovery, huh? This is MIT, you see in the background there, that's the main MIT building, and this is part of our, what we call the Great Court. So robotics, once again, robotics wouldn't be anywhere near possible without power electronics. So another technology that is rapidly advancing is the technology of batteries. And of course, it's the electric vehicle that has motivated all of the research on batteries. And every time you have a battery, you have power electronics. Even the LED flashlight is power electronics, because the LED is a power electronic device. But Tesla, I won't go through, I'll show you a number of different, again, news announcements about battery technology, just to illustrate how ubiquitous the research on batteries is today, and how much hope there really is for battery technology advancing substantially from where we have it now. So Monash University claims they've got a lithium sulfur battery that doubles electric vehicle range. Silicon anodes are another technology to advance the lithium ion capacity. Lithium metal batteries are technology that people are exploring once again. And John Goodenough, who was actually the inventor of the lithium battery, has a claim that there's a glass battery that actually gets better and increases its capacity over time. Now, if you know anything about battery technology and the announcements about battery technology, you know that battery technology announcements are always super optimistic. So I would be very careful about interpreting a lot of what you read in the paper as being gospel. But what it does indicate is that there's a tremendous amount of research going on to advance the technology of batteries. Here's another challenge for the future, 5G. Everybody's talking about 5G cellular systems, cellular mobile phones. The problem is that a 5G base station with 128 antennas, I don't know if you're familiar with what 5G represents, but a 5G has a macro cell base station with lots of antennas. And if you have 128 antennas on it, it's about a 3 kilowatt load. 3 times the number of LTE base stations are needed to cover the same ground as current LTE covers, which means you've got, and each one is 3 times the power consumption of an LTE base station. Now, those are statements from China Mobile, which of course is a major mobile carrier and mobile technology developer. Some people have taken issue with this. Some people have taken issue with the number of antennas that you need. But the point I want to make here is that 5G is going to require a lot more power than current LTE requires. And that means a lot more power electronics and a major focus on efficiency. Yeah. Yep. So I want to, I don't know how I got here. Hold on a second. Yeah. Okay, so now what I'd like to do is show you just a few technologies, semiconductor technologies that have made a significant impact on power electronics. The first is the superjunction MOSFET. And for those of you who don't know how a superjunction MOSFET operates, I'll give you just a very short description because I think it's really quite fascinating. The superjunction MOSFET differs from the conventional vertical MOSFET by having in the drain region here columns of N and P materials. So you have an N column, a P column, an N column, a P column, etc. And you have the gate regions and the oxides, of course, extending into the N drain region. Now, what happens here is going to be illustrated in the next slide, and I'll try to explain to you why this gives you a much less resistive, why it allows this region, this drain region, this extended drain region, to support a much higher voltage than it would if it was strictly all N, which is what a conventional device is. So if we look here, And these are sketches that I made that are going to go eventually into the second edition Principles of Power Electronics when they're refined. But what I show here is on the left here is the conventional drain region of a MOSFET. So here you have the P plus, and then the N drain, and then the N minus contact. And if you put a voltage across this, what you see is an electric field. And of course, this is in reverse bias. You see an electric field which starts out, depending upon where you want to start, from the, let's start here. You're starting here at 0 voltage. And then of course, as you go up here and you apply Gauss's law, you've got, of course, all these positive ionized donor sites, which represent the charge in this region. And the electric field is then triangular and reaches its maximum at this junction. And of course, this is a very heavily doped region. And so since this is a negative charged region because it's got ionized acceptors, the electric field then collapses in a very short region. So the voltage that you can support across this column is essentially the integral of this triangle. Now, if I take and reverse if I take now and make this region a P minus region instead of an N minus region, then this region in here has negative ionized sites. And if I do the same analysis, I see that I start here with 0 voltage and using Gauss's law, since this is just a uniform region of negative charge, I get an electric field that looks like this. Again, a triangle, but in the opposite direction. Now what I do is I bring these two columns together, as you see over here. Now, when I bring those two columns together, there's an interface between this N minus and P minus region. And Maxwell's equations say that at this interface, the electric field has to be continuous. And if you look over here, the equipotentials, the equipotential across this region has to be continuous. These equipotentials differ substantially from one column to the other column. But if they're forced to be continuous, and if the columns are narrow enough, then what happens is that the field distribution becomes something like this. It becomes rectangular. And so for the same dimension, I now have a rectangle that has twice the area of this triangle. And therefore, for the same dimension, I can support twice the voltage. And it actually gets a little better than that, because I can also increase the doping concentration in these columns if they're narrow enough and still maintain the continuous equipotential across this boundary. And so not only can I support a greater voltage here, but I also have reduced the resistivity of this region when it's conducting. So that's the basis of the superjunction MOSFET, which has, to a large extent, displaced the conventional MOSFET. So what else is happening with semiconductors? Well, here's a materials chart of materials that are used for power semiconductor devices. Of course, we all know silicon, germanium, and now we have gallium nitride and silicon carbide, which are the wide bandgap materials. And these have a bandgap that is about 3 times silicon. Forget germanium, we don't use germanium anymore. But relative to silicon, we have gallium nitride and silicon carbide, each have about 3 times the bandgap, which means that their intrinsic concentration is very low. So leakage currents at junctions are extremely low. The devices can operate at much higher temperatures. And furthermore, with respect to silicon carbide, the thermal conductivity is almost 3 times what it is for silicon. And so the combination of this bandgap, the increased breakdown field, this breakdown field is increased by a factor of 10, means that we can increase the voltage rating of a device for the same dimensions, or we can keep the voltage rating of the device the same and decrease the dimension, the vertical dimension, by a factor of 10. This is really, really powerful stuff. So let's consider what happens here. So if we have a 3.3 electron volt band gap versus 1.1 for silicon, we can go to much higher temperature operation. If the band gap is, if the breakdown field of the material is an order of magnitude greater than it is for silicon, we can reduce the dimension of the drain region of a FET by a factor of 10. We can also, if you think about this carefully, if we want to support the same voltage, we can increase the drain doping by a factor of 10. So the combination, thinner drain, factor of 10, increased doping, factor of 10, theoretically, we can decrease the on-state resistance by a factor of 100. Now that's in theory. Of course, there are other elements to the on-state drop that aren't included here. But what it does show is that silicon carbide for a power device has immeasurable benefits. In addition, with a thermal coefficient of resistance with a thermal coefficient of sorry about that. It's my finger on my mouse. With a thermal coefficient of resistance of, thermal coefficient of conductance of 3.6 versus 1.5, we can operate a silicon carbide device in a much higher ambient temperature. So what about gallium nitride? Well, gallium nitride is a much more expensive device. The biggest issue with gallium nitride is that it's epitaxially deposited on a substrate of silicon or silicon carbide or aluminum oxide, Al2O3, which is sapphire. This is because you cannot fabricate so far a native gallium nitride substrate of sufficient thickness to be able to fabricate a vertical power device. So all gallium nitride devices are lateral, not vertical devices. They have a low threshold voltage, so you can switch them quite fast. The electron mobility in the channel at the interface between the aluminum gallium nitride and the gallium nitride results in what's known as a high electron mobility transistor, which also enhances the switching frequency. So gallium nitride devices are used at very high frequencies, but at low to moderate power applications. In those applications that can afford the additional cost of gallium nitride, the device has substantial advantages. But again, it is an expensive device. So, what I'd like to do is conclude with a few thoughts. You know, as power electronics engineers, we're currently blessed with extraordinary opportunities and some very exciting challenges. To exploit the opportunities and to meet these challenges, we have to continue technology development and meet the challenges by expanding capabilities of semiconductor devices, advanced passive component technologies, which is another limitation I've not discussed, and produce new magnetic materials. We have to invent new manufacturing and packaging technologies. We have to drive to higher frequencies. We have to exploit new battery chemistries. And more than anything, we have to recognize nascent application opportunities as they arise. In 1984, I was honored to give a lecture at the IEEE Centennial Convocation at the Franklin Institute in Philadelphia. The night before my talk, I was watching a local TV news program that was reporting on the convocation. And there was a 7-year-old boy that was being interviewed on the program. And the convocation was held at the Franklin Institute, which is essentially a museum of technology. And he had been visiting the museum during the convocation and had been experimenting with the Van de Graaff generator. You know, the museum had a lot of hands-on exhibits. And he was fascinated by what it did to his hair. It made his hair stand on end. And the reporter asked him, what was causing his hair to stand up? Electricity, the young boy answered. What is electricity? The reporter asked him. And his answer, his answer, electricity is very powerful and can do almost anything. It is power electronics that makes electricity do almost anything. And that's a quote from a 76-year-old MIT graduate. So thank you very much for your attention. I hope that I didn't go over too long, and I'm really happy to answer any questions anybody has.
Thank you very much, Professor Kassakian, for your excellent presentation. We will move to the questions and comments. Let me say first that as far as I see in several of the platforms, there is too many comments from the audience congratulating you for the conference and asking for a copy of the slides. Too many asking a copy of the slides.
Well, they're welcome. As you know, you can use the slide.
Yeah, I have the file. If you need to update, I can wait this afternoon for the final version, and then we will send to all the persons who asked for the slides. Okay.
Yeah, you have the final version.
Yes.
Do you have it now, or do I have to send it to you?
No. You had sent me.
Okay.
Okay. Let's move to the questions and comments. We will start with Zoom. Could you please, Mario, share with us the questions or comments from the audience?
Of course, Professor Arau. First of all, thanks a lot, Professor Kassakian, for your excellent presentation. You deal about many topics, very, very interesting. We have some questions for you here in some platform. And the first one is from Professor Lobardo Cortés from Instituto Politécnico Nacional. He asked you about what is your opinion with respect to the materials used in power devices? What is expected from silicon carbide and gallium nitride in the medium term?
Well, I think silicon carbide is already being used in commercial devices. You can buy silicon carbide Schottky diodes, which are very, very good, up to 1,300, almost 2,000 volts, which is, of course, as you know, much higher than silicon Schottky diodes. You can get silicon carbide MOSFETs. You can get silicon carbide IGBTs. So they are already commercially available and excellent devices. And as I showed you, they're being used by Tesla and many other companies that have high performance machine drives and other apparatus. Gallium nitride is being used in relatively limited applications that are at very high frequencies, above tens of megahertz. And those are generally low power applications such as the wall adapters, where you adapt the, for charging batteries on your iPhone or your computer and so forth.
Okay, thank you. We have another question from the same person, Leonardo Cortés. He asked you about, there are data on whether gallium nitride will reach similar voltage value to silicon carbide without losing high switching?
No, I don't think it will, because silicon carbide, one of the parameters of silicon carbide that is not compatible with what you can do, I'm sorry, one of the parameters of silicon nitride, which is not compatible with what you can do with silicon carbide, is the, I'm gonna find it. What did I do with my, it is the, yeah, the thermal conductivity. The thermal conductivity of gallium nitride is approximately the same as the thermal conductivity of silicon. So you will not get the same thermal benefits with silicon carbide that you will with, I'm sorry, with gallium nitride that you will with silicon carbide.
Okay.
I also think it's going to be a long time before we have silicon carbide, I keep getting them confused, gallium nitride as a native material that will not require a substrate and an epitaxial deposition in order to fabricate gallium nitride devices.
Okay. Excuse me, about the same topic, we have two more questions. For example, Ricardo Ramirez from CENIDET asks you about, in your opinion, what is the best semiconductor material regardless of price?
So,
about same question, what is your opinion about graphene, for example?
Graphene, first of all, graphene is, we do not have graphene power electronic devices yet. Graphene is being explored for integrated circuits to some extent and as interconnects in devices, but I've not seen any research results relating to power semiconductor devices using graphene. I think it's going to be a long time before gallium nitride overtakes silicon carbide as a device for power electronics. I think the benefits of silicon carbide are just too great. And so I would say in the foreseeable future, it will be silicon carbide, not gallium nitride, for applications that require any reasonable amount of power and voltage. If you're going to, by the way, if you're not going to go above 600 volts or so, it probably doesn't even pay to use silicon carbide. You would use silicon devices. Right?
Okay.
You have to understand the benefits of silicon carbide in order to trade off silicon versus silicon carbide, because silicon is still a very cheap alternative to silicon carbide.
You're right. Thanks a lot, Professor Kassakian. We give an opportunity of the other platforms to ask you some questions. Thank you.
Okay, that's the end of the questions.
No. We give opportunity for the other platforms,
Okay.
Facebook and YouTube. Please, Dr. Arau, which platform is the next? Do you, Dr. Arau, you have your microphone turned off?
Yes.
Okay.
Sorry.
Thank you.
Thank you, Mario. As far as I know, in Facebook, we don't have any question. Is correct, Ricardo?
Hi, that's correct, Dr. Arau. First of all, I would like to thank Dr. Kassakian for his interesting presentation. And well, at this moment, we don't have any question on Facebook. We will start maybe with the YouTube. I don't know.
Okay, thank you. Alfredo, what happened with the YouTube question or comment? Is there any?
Yes, thank you very much for your conference, Dr. Kassakian. Yes, I have we have a question in this platform. Two questions. Wait a minute, please. Ignacio Morales don't give information about your institution, but your question is, what role does graphene have in power electronics in the medium and long term? En Spanish, ¿qué papel tiene el grafeno en la electrónica de potencia a medio y largo plazo? Is the question.
Okay, I didn't quite understand that, Alfredo.
Dr. Kassakian, the question is about graphene. Do you answer this question yet?
Graphene?
Yes, it's the same question about graphene. What is your opinion about graphene?
Oh, I don't see graphene being used in power semiconductor devices. Graphene is being used in power electronics. I think the place where graphene has the most potential, and this is in the future, is in battery electrodes and in electrodes for double layer capacitors, supercapacitors, ultracapacitors. I think those are the places where graphene will have a role to play. And as I said earlier, also perhaps in semiconductor interconnects.
Thank you. Thanks a lot, Professor Kassakian.
Okay. Go ahead, Alfredo, with the second question, please.
Yes. Wait, please. where don't say the name, but the question is, where can I learn more about those solid state transformers?
Okay. Well, I think the best place to learn right now is in the IEEE transactions on power electronics, or the IEEE transactions on industry applications. If you are patient, after the second edition of Principles of Power Electronics is published, you can learn about it in that. But, but right now, I don't know of any easy place to learn about solid state transformers except by looking at some papers in those journals. You should use IEEE Explore. I would hope everybody is a member of the IEEE. And if you are, or if you belong to the university, you probably have access to IEEE Explore, which allows you to go to any of the journals and access articles, look up articles by topic and access them. And actually you can print out a PDF of the article. So unfortunately, with solid state transformers, I think that's the only resource at present.
Thank you very much.
Okay.
And the last question is about the user of name frequencies. What your question is about? I don't know if you can respond. What is the purpose of the 5G right now?
What is the what of the 5G?
Yes, the 5G right now.
Oh, what's the status of 5G right now?
Yes.
There's a lot of there's a lot of publicity about it, but as far as I know, it has not been really deployed anywhere for people to use. And I know phones yet that use 5, even though they say they use 5G, it's some subset of 5G, I believe, that they are capable of employing. So 5G is still a ways away.
Okay, thank you.
That's not my expertise.
Yes.
That's all the question in this platform.
Yeah.
Okay, thank you very much, Alfredo. Let's move again to Zoom. Mario, could you please share with us?
Yes, we have a lot of questions for you, Professor Kassakian, here in Zoom.
Okay.
We have one question about from Binji, and he asked you about, this is a very personal question, I think. What is the equipment behind you, Professor? Why is it so important being the only one on your desk? the equipment behind you, the black equipment.
That interesting question. That is a pre-World War II radio receiver, shortwave radio receiver. And I used that when I was an amateur radio operator. When I was a ham radio operator, that was the receiver that I used. My father had that after he came back from the Navy. I don't know where he found it, but he had it. And then I used it in my radio station. It's a beautiful piece of engineering.
Very interesting,
and it weighs about 40 pounds.
It's a museum piece. This Thanks a lot. I have another question from the same person, but this is a technical question. Is why do we not see the superjunction silicon carbide MOSFET? It is because that the drive region is much shorter and the benefits is less than is.
I'm sorry, Mario, I didn't, why do we not see what?
Yeah, about the question is about the, let me see, the superjunction silicon carbide MOSFET. Why is the reason this MOSFET with this material is not in the trade, in the market?
As a superjunction MOSFET.
Superjunction MOSFET is okay.
Yeah, I don't know, but here's my thoughts on it. To make the superjunction is not easy. So a superjunction transistor is a little more expensive to manufacture than a conventional transistor. And to make silicon carbide transistor is already an expensive process. So I just don't know if the ability to dope columns of sufficient thinness in silicon carbide can be done. So that's just a guess. The person who asked the question is correct. I have never seen a superjunction silicon carbide device, but I don't really understand the reasons why. So it's just my opinion as to why we don't see it. And maybe someday we will see it.
Okay, very interesting question. I have more question, Professor Kassakian. Let me tell you. We have a question from Professor Carlos Aguilar from here, from CENIDET. He asked you about the renewables power source penetration into utility grade intermittent power sources mainly makes necessary to use energy storage systems. According to your experience, what you consider is the best energy storage technology for these applications?
I'll tell you what I think is the best, but maybe not the most practical, is pumped hydro.
Okay.
Okay, but there's very limited opportunities to create new pumped hydro stations. You know, people are using batteries, which today is probably the most practical storage mechanism. Flywheels, there are some companies that are trying to make flywheels that are capable of storing sufficient energy to be practical. For very short periods, that's okay. It's the biggest problem to be solved with renewable energy. Without a doubt, storage is the biggest problem, the most challenging problem that we need to solve in order to make renewable energy practical on a much larger scale than it is today. So it's a very good question. I do not have a good answer.
I agree with you. Other question about batteries from the same person, from Carlos Aguilar. What is your opinion about the redox flow battery technology? The redox flow battery technology, energy storage element. What is your opinion about this kind of storage?
Yeah, there's been a lot of work done on flow batteries, and I'm not a battery expert. All I can say is that I have not yet seen a practical flow battery deployed commercially for an energy storage system. There are certainly some advantages to flow batteries. But I think that the technology of flow batteries and some of the logistics, the infrastructure required for flow batteries is more complicated than it is for conventional lithium-ion batteries. So I guess a simple answer to the question is I really don't have an opinion as to whether they will eventually become a practical element of an energy storage system.
Okay. Before to give the opportunity to other platforms, I have a question, a personal question for you about a very interesting topic that you mentioned in your conference. It's about, let me see, the electroaerodynamic propulsion. This topic, I used to see a paper about the MIT in the Nature Journal, and I think this is a very interesting investigation. Could you give us more details? And is there any company involved in this investigation?
Is there any company involved with this? Is that your question?
Is there any company working with you in this research?
No, this is, I have to say that the main research is being done in the Aero-Astro department, and I believe that it is being funded by the Department of Energy. It is not being funded by a company. So does that answer your question, Mario?
Yes,
Yeah.
Is my question. Okay, I give the opportunity to other platforms to do some questions for Professor.
Okay, Mario, before you do that, I just have another comment. The person who wanted information on the solid state transformers,
Okay.
if he or she sends me their email with a request, I will send them some papers.
Excellent.
Okay.
Thanks a lot, Professor.
Yeah.
We have your email and we give the email to people interested in this topic. Okay, thank you.
Yeah.
Okay, thank you, Mario. Let's move to Facebook, because
Thank you so much.
I know Ricardo has new questions or comments.
Thank you so much, Dr. Arau. Dr. Kassakian, we have comments and also we have some questions. Let's start with one comment that I had. Eduardo Hernandez said, thanks for the conference. And well, let's continue with the questions. Aaron Shaun Aguirre said, what is your opinion about advance in solar panel technology? How can it be innovated?
Well, I don't work in solar, but the solar has amazed me in terms of how efficient solar panels have become relative to what they were 10 years ago, and also how inexpensive they've become. In large measure, of course, to China manufacturing the solar panels and essentially dominating the solar panel market. The future of solar panels and solar energy relies upon a couple of things. The primary one is how the local utilities plan to integrate solar energy into the grid. By that, I mean, if you have solar arrays and you're generating energy and you're feeding it into the grid, how much is the utility company going to pay you for that energy? And that varies in the United States, that varies from state to state. Some states are very aggressive. It's very favorable to put solar panels on your house. In some states, they have very large solar farms. Some utilities themselves are engaged in producing solar farms. So that's one. So it's the regulation and the law and the rules, financial rules regarding recovery of capital and the payment for energy. The other is what is the cost of installation of a solar system, and that has of course come down, and there are companies that will install it for free if the incentives associated with the recovery revenue are favorable. So a company will come and they will put it on your house, install the whole thing, and they somehow get back their costs through a revenue sharing agreement. And I think that the future is that solar will become more and more a feature of part of the renewable energy portfolio, especially in those parts of the countries where there's lots of sun. I mean, in Mexico, you must have lots of solar. Yeah.
Okay, thanks so much. We have another question. This one is from Instituto Tecnológico de Matamoros, and it's for Daniela Abigail, and she said, "Hi, good afternoon, Mr. Kassakian. Since you are more experienced on this field than us, and you mentioned Alice airplane and its huge battery, I was wondering if you have a prediction on how much time are we gonna take to make some kind of a smaller beta battery that doesn't lose performance, and what path in materials are we gonna take for that matter? As a relatively new student in university in chemistry career, I am interested as well of how can we contribute in the research of that kind of materials."
That's a really good question, and I wish I could answer it, but I showed you a whole bunch of different announcements of different chemistries, and every one of them had big promises of performance improvement. So I think that what we're talking about is a lithium chemistry of some sort. And it amazes me that there are so many different ways of creating a lithium battery. The electrode structures, especially the cathode, has a major impact on the performance of the battery. And so the cathode chemistry is very critical, and people are working on different chemistries for the cathode. One of them, of course, is carbon nanotubes. What was this student, remind me, Ricardo, was this student a student of chemistry, or was she in power electronics, or what?
She's in chemistry.
Chemistry, great.
Chemistry.
Yes, tell her
She's a new student. Maybe she's in her first year, or I don't know.
Yeah.
It doesn't say, but she's a new student.
Yeah, well, I think that batteries is a wonderful opportunity for her to work on. I think there's a lot of work going on, and I'm sure there will be major advances in battery chemistries.
I consider it too.
But chemistry was my worst subject as an undergraduate.
Me too, but passing another question, we have one for Daniel Zapata, and he said, "Good afternoon, Dr. John Kassakian. On MOSFET technologies, what is the difference over DMOS and SJ MOS? Since it is assumed that they tend to have a high drain to source resistance per unit area of silicon and come with relatively high drain source resistors.
Well, the DMOS is just a generic term for a double diffused MOS structure, which is a vertical structure. And I could, maybe I could pull up a diagram to show you, but actually, let me see. Let me just see if I can pull something. Hold on 1 second.
Okay, of course.
Yeah. So. Yeah, okay. Wait 1 minute. Yeah. Okay, so let me share my screen. Let me see. Okay. So can you see this?
Yes.
Okay, so this is a DMOS structure. Okay, and here's your drain region.
Mm-hmm.
And of course, the resistance is due to a number of things. There's a resistance associated with a channel, which is right here. There's a resistance associated with the neck, what we call the neck region, which is here, where there's a current crowding, there's current crowding in this region. And then, of course, the current spreads in what's known as the extended drain, which is this region. Now, the extended drain region is, let's consider it completely depleted. And I'm sorry, we're in forward conduction. So we have a resistance that's associated with its doping concentration. And the doping concentration is limited by how thick we can make this and what the voltage is we want the device to support. In the case of the SJ FET, this region is divided into these N and P columns. And as I showed you, the interface between those columns forces the electric field in this region to be uniform, which is not the case in the DMOS structure here. In this structure, the electric field starts out at 0 up here and a maximum down here at the drain. With a constant electric field, we can support much more, twice as much voltage. And then we can also increase doping density in this region, in the SJ FET, and therefore reduce the resistance because we have reduced the resistivity of the material, the doped material in this region. So the SJ FET and the DMOS are not similar in terms of their on-state resistances. If you have two devices and they have the same on-state resistance, one's an SJ FET and the other's a DMOS, if you look at the device areas, you'll probably find that the device areas, the device area of the SJ FET is smaller. So I'm not quite sure what the what the questioner had in mind, but does that answer it or not?
Well, they refer something about the resistance per unit area, but well,
but it's not the same.
No.
No, I don't. It won't be it's not the same. unless I'm missing something. So if the questioner has some information, then maybe he or she could send me an email with it, and because I'd like to know.
Mhm. We will give to all of our public that you email, Dr. Kassakian. And well, we have another question, but I consider that this is the turn of the YouTube platform. So, Dr. Arau, I don't know, we continue with. Thank you so much, Dr. Kassakian.
Sure, yeah. We can continue. It's okay with me.
Okay. Alfredo, do you have another question or comment?
Yes, we have another questions. From the Technical Institute of the Madero, the Professor Roberto Galindo del Valle. He has a comment about the Professor Kassakian. The next, your 91 book is a very good one. I really love it. Thanks a lot for sharing us your expertise and conocimiento, knowledge. I really wish you good spec. Is your comment.
Thank you.
Another comment is another question. Bing Yi does give information about your institution. The question is, cosmic rays plays a role to cause transistor catastrophic failures. What are the preferred material for aerospace and space applications?
Well, again, I'm not an expert in that area, but the wide bandgap materials, of course, would be more immune to ionized radiation than silicon. And I think silicon carbide is being used in space, although I'm not absolutely sure. It's not really my area. I don't know how they harden some of these devices. Some of them create traps that will enable the ionized carriers to get trapped instead of causing failures. But it's really out of my area of expertise.
Don't worry, Professor. I know the questions are difficult. And the third question is more difficult. It's really personally. The participant is Sandy Kaller from the Rierson University. Your question is, knowing all that you do know, what advice would you give to your younger self if you could go back in the time? Yes, do you understand my question?
I didn't. I'm sorry, Alfredo. I didn't understand that. Is that from Sandy Keller?
May I help you, Professor? The question is about a personal question.
Si pudiera retroceder en el tiempo, ¿cuál sería el consejo que... A ver, permíteme, por aquí la traduje.
Let me ask the question. What is one piece of advice you would give to your younger self if you could go back in time? Advice for yourself in the past.
Okay. First of all, did you tell me that the questioner was Sandeep Kaler from Ryerson University?
That's correct, isn't it, Alfredo?
Yes, it's the question of Sandy
Oh,
Taylor.
I don't, Sandeep is drawing all the figures for my new book. So I don't know how he found out about this celebration. Anyway, it's a good question. It's an excellent question. Let me answer it in a slightly complicated way, because when I started out, there was no internet. There was no cell phone. There certainly was no iPhone. There wasn't even a personal computer until very early. And as a consequence, there was much less distraction from some of these new technologies. What I really miss is, I guess, the silence. Silence in the sense of not constantly being inundated with emails, which is a terrible distraction. I mean, you feel you have to look at your emails every 10 minutes, or you keep getting dings if you don't turn them off. There's a sense that people expect an immediate response to a question. You're not free on the weekends because the internet has you tied to your computer all weekend. I think if I were to give somebody entering the field today advice, not a comment on what I would have done when I entered the field, what I would have done differently, 50 years ago, but for somebody entering the field today, I would say, try as hard as you can to avoid the distractions and disruptions created by the communication technologies that we have been forced to accommodate. Because today they prevent you from interpersonal interactions in a way that for many years after I joined the faculty was the way of life, where you met your colleagues every day for lunch, in the office, in the laboratory. Today, many faculty members spend half their day on their computer, and that doesn't create interpersonal discourse. It doesn't help the creation of new ideas through interpersonal discussions and give and take. It's something I really miss. If I want to meet with one of my faculty colleagues today, one of my young faculty colleagues, I have to make an appointment a month in advance sometimes. That's crazy. It used to be that you call up on a telephone and 5 minutes later you were sitting down talking with somebody. So I guess my advice, Sandeep, and we can talk about this together, I'd be happy to do that, is somehow try to create some space for yourself to think, some space for yourself to find other people in a similar situation and engage in constructive interactions. I guess that's really what I think is missing today. The other thing that I guess the one thing that I would say I would do a little differently if I were starting again back, and I was back then, is I would maybe spend more time with my family. That's always a problem for young faculty members. Yeah, I guess that's probably,
Okay.
you know. So sorry for the lecture, but that's something that I feel very strongly about.
Okay, thank you very much,
Thank
Dr.
you very much,
Kassakian.
Dr. Kassakian.
I think
Hay otra pregunta.
we think that we need to close the.
Ok, está bien.
There is at least probably 5 or 7 questions or comments, but as we mentioned at the beginning, we will make 2 rounds of questions from each platforms. I think that is time to close. Sorry about it. Before I present a diploma of appreciation that we want to give to Dr. Kassakian, let me make a couple of comments. Next week on Friday, we will have another conference, in this case from the computer science department. The conference will be given by Dr. Olivia Fragoso. The title of the conference is Extensibility and Limitation of Software Engineering. And concerning the Power Electronics Conference, I saw some question about this at the Zoom platforms. Unfortunately, we don't have a date, but we can say is that Dr. Fred Lee, Emeritus Professor of Virginia Tech, USA, and Dr. Prasad Enjeti from Texas A&M University already accepted our invitation to give a guest lecture in the future. Please keep on touch with our social network. We will be making or giving all the information about those conference, which is already confirmed. So let me share now my screen. I would like to present all of you, and especially for Professor Kassakian, this certificate of appreciation, from the National Technological of Mexico through the National Center of Technological Research and Development, CENIDET, due to, or for Dr. John Kassakian, Emeritus Professor from the Massachusetts Institute of Technology, USA, for giving the conference Power Electronics, Where Are We Been and Where Are We Going? In the frame of the 2021 Virtual Colloquium Conference of CENIDET and the cycle of International Power Electronics Conference, which is in charge of the Power Electronics Group at CENIDET. The certificate of appreciation is signed by Dr. Jessica Imelda Saavedra Benitez, General Director of CENIDET. Thank you very much, Professor Kassakian, for your kindness and for accepting to share with us your experience, your knowledge, yes, and it was a great honor, of course, to receive your visit and to have your talk. Too many students and researchers from several parts of the world. The information that I received was that a little bit more than 350 attendees attend your conference, considering YouTube, Facebook, and Zoom platforms. Thank you very much, Professor Kassakian. A few minutes ago, we sent you this diploma of appreciation. It's a small present, but you know, we strongly appreciate all your kindness, and you decide to share with us your experience and your knowledge. Finally, Dr. Kassakian, I would like to ask you if you want to give some final words in order to close the conference.
Yeah.
Let me.
Yes.
Disconnect.
First of all, I want to thank you again, Professor Arau, for this very kind invitation. I've thoroughly enjoyed the opportunity to interact with all of the participants who have been on this conference. I did receive my certificate thanks to technology. I've already got it, so I'll put it in a frame and put it on my wall.
Thank you.
I especially enjoyed the questions. I think they were excellent questions. I wish I could have answered all of them. And I hope, I really enjoyed my visit there in 1993. I hope that after all this COVID stuff is over, I'll have an opportunity again to visit Mexico. As I said, I've only been in Mexico once, and it's our neighbor country. I'm very surprised that I haven't been there more frequently, but I hope that before I can no longer travel, I'll get an opportunity to visit you folks at Sanidad again.